Okay, we got it to Friday. Last section. So hopefully I've spoken to you a couple times this week as before you watch or as you're watching this, and we figured out that schedule. Let's see, on Monday we're going to do a chapter review. I will produce a video going over maybe not every question of the chapter review, but definitely every section. And remember, my tests are, with exception of a proof or a word problem, my tests are exactly like the practice test. Okay, so here we go. Last section. Now, here's your homework. I don't want you to get too intimidated. Every one of these is a word problem, and the word problems will require you to draw a picture in order to get a full understanding of what's going on here. All right, so here we go. So applications of right triangle trig. If you were to ask anyone who uses math in their job on a daily basis, I would bet you, other than maybe an accountant or something like that, but anyone who deals with physical objects is probably using trig of some sort. How do we know the actual distance between the Earth and the Moon? We've never actually used a stick measuring device or a string to measure that, or the distance between us and the sun. Those are all calculated, many techniques, but one of the primary techniques is to use trigonometry in order to do those calculations. So even though I'm going to show you an example of this today, there are many examples. All right, so a quick review. Remember, we're doing trig. There are three basic trig functions: sine, cosine, tangent. Each one is by definition a specific ratio. The ratio of sine is opposite over the hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and we get that expression SOHCAHTOA to help us remember those three trig ratios. So trig allows us to do many things, but the two that we learned for this year are to solve for an unknown side length and to solve for an unknown angle measurement. So for solving for an unknown side length, you must be given one angle and one side. The process is examine the angle that you're given, in this case, 56 degrees. The relationship between the known side and the unknown side, or the unknown side in this particular example, is the opposite side to 56 degrees, and 36 is the adjacent side to 56 degrees. So let's see, opposite adjacent, which trig ratio is that? Opposite adjacent is tangent. So that's my setup. So opposite over adjacent would be y over 32, multiply both sides by 32. You've done this many times now. 32s cancel on the right side, and the left side is what we plug into our calculator to get our final answer. Solving for angle measurement, remember, we're going to use the inverse function for that. So here's a triangle, right triangle here with an unknown angle x, and it has to give you two side measurements. So the relationship between that unknown angle x and the two sides, 3 is the opposite side, 6 is the hypotenuse, so that would be opposite over hypotenuse. That would be inverse sine. So remember the initial setup, if we want to go through the entire algebra here, would be sine of x is equal to the opposite side divided by the adjacent side, hypotenuse side. I'm sorry, I'm thinking tangent. And then to solve for x, we would have to get rid of the word tangent. So we would do the inverse tangent of both. I'm sorry, alarms going off in the background here, and I'm confused me here. Inverse sine of both sides. So we take the inverse sine of both sides. Inverse sine and sine cancel each other out. So you're left with x, and that is equal to the inverse sine of 3 over 6. And that is what you plug into your calculator. Okay, so plug that into your calculator, inverse sine of 3 over 6. Notice 3 over 6 is a half. You could also type in 0.5 and you'll still get 30 degrees. So that's a quick review. Let's see some real examples, word problems, of how trig is used. So I gave you the wind up at the start of class, but when you're measuring things or you're making things, trig is a really powerful tool for solving for unknown sides and unknown angles. So here is one of many examples. And I will say, as a math teacher, almost all of the examples you see in a math book involve something of height, So say a building, a flagpole, an airplane. For some reason, we like lighthouses, sailboats. So you need something a distance away from it. So before we get into an actual example, I'm going to introduce you to two vocabulary words. So here's the idea. Let's say you are at ground level and you want to look at something at an altitude. So it could be a mountain, could be a bird, could be an airplane. We like to use buildings and towers. So there's the Eiffel Tower. So as you look to the top of the structure, well, the first thing naturally would be to go from the horizon to the top. So I'm going to key in on this. You would look to the horizon first and then to the top of the object. And that angle that forms right there, theta, with the tower itself makes a nice right triangle. So it turns out that we can actually calculate the height of any object as long as we know one of the angles and one of the sides. So let's say we want to calculate the height of the Eiffel Tower. Well, if you went to the base of the Eiffel Tower and just walked off a certain distance and then took a protractor and measured the angle that you were looking to the top, well, you could actually solve for the height without actually going to the top or actually doing any direct measurement of its height. If you ever notice construction workers, there's always someone looking through a small telescope-looking device, and they're creating an angle. This is one of the things that they can be doing, is taking measurements using trigonometry. All right, so back to our new idea. Our new idea is, what are we going to call this angle? The angle that's formed when you're looking at an object in the sky or up in the air by starting looking at the horizon first and then looking to the top. That is going to be called the opposite of if you were looking from the top to the horizon down to the bottom. Yes, we're in France, so I gave a girl with a beret and a sack of baguettes there. So this angle right here would be the opposite, or geometrically speaking, it would look like it's the opposite of the one that we just drew. And it turns out that those two angles, the angles looking to the top and the angles looking to the bottom, are related. And they have words, descriptive words for those two angles. So this angle that's formed by looking at the horizon to the top is called the angle of elevation. You had to elevate your eye to look to the top of the Eiffel Tower. And the opposite of that, if you're at the top of the Eiffel Tower looking at the ground, you would look to the horizon first, and you would, look down to an object. We don't call that the angle of down. We call it the angle of depression. So once again, these are not theorems. These are simply definitions. So tonight's word problems, all of them will talk about either the angle of elevation and the angle of depression. And I will say, of the two, almost no one screws up the angle of elevation. Everybody screws up the angle of depression, and I'll try to describe why. All right, so it can be confusing, especially the angle of depression. So try not to get too confused. All right, so here's an example. You're in a sailboat, and off in the distance, you see a lighthouse, and you would like to know how far is the lighthouse from my location. So sailors use nautical charts. You look on your nautical chart, and the chart will always tell you how tall objects near the coastline are, and you could form an angle of elevation. You have a device on your sailors will have a device to measure angles that they see, and you could measure that angle between your boat to the top of the visual distance, or the visual angle between the bottom to the top of the lighthouse. That would be the angle of elevation. And as I said, most people don't screw this one up. So we look at the chart, and it would tell us how tall it is. Now, reverse roles here. You're at the top of the lighthouse looking at the sailboat, but remember, you must look to the horizon first. The issue is that some people would call that angle right next to the lighthouse, where the yellow is, that would be called the angle of depression. That's not true. The angle of depression would be there. It wouldn't be in the other location. It would be there. So on both cases, angle of elevation and angle of depression, the key there is the red and the blue line. And that's your first step. And that is to look at the horizon first before you draw that other line to create your angle. All right. Now, interestingly enough, the angle of depression and the angle of elevation do have a relationship. So let's see, what's the relationship? Well, the blue line and the red line are parallel. The black line could be considered a transversal, and those are alternate interior angles. And so therefore the angle of depression is the same as the angle of elevation as long as your frame of reference changes. So we would say the angle of elevation from the sailboat to the lighthouse is equal to the angle of depression from the lighthouse to the sailboat. All right, so that is the relationship. So the angle of elevation to an object equals the angle of depression from an object. All right, and I usually open this up to class and see who's the smarty pants who can figure that out. All right, so on to the example. So many of the examples simply take this, I don't know, this format right here and simply substitute different objects in the sky or on the ground. In this case, I'm going to focus specifically on a sailboat and a lighthouse, but you could equally substitute a bird or a flagpole or a shadow, any of the things that would be in the sky or on the ground. So it says calculate the distance between a sailboat and a lighthouse. So if it's the distance between a sailboat and a lighthouse, then your sketch should contain a sailboat and a lighthouse. Now, you don't have to actually draw those. You can have little sticks representing each one. That'd be fine. So calculate the distance between the sailboat and the lighthouse. If the lighthouse is 25 meters tall and the angle of elevation between, and read this carefully, the angle of elevation, so horizon to the top, between the sailboat and the lighthouse is 2 degrees. So angle of elevation is found by looking to the horizon first and then looking up. So there's your 2 degrees. Now, there's no question mark here. It says calculate the distance between the sailboat and the lighthouse. So we're calculating the blue line right there. So how would it read if we were calculating the black line? How far is it between the sailboat and the top of the lighthouse? That would be the black line. But if it's just the distance between the sailboat and the lighthouse, that would be the blue line. Okay, so the most challenging part of trig word problems is simply the setup, the drawing of the picture. The actual trig is pretty rudimentary. So let's see, we're trying to calculate the distance between the sailboat and the lighthouse. That's our x. And then we simply see what the two sides are in relationship to angle 2, or sorry, the 2 degree angle. So let's see, the 25 would be the opposite side. The x would be the adjacent side. Opposite over adjacent is tangent. Okay, so let's see, set that one up. Tan 2 would be equal to 25 over, oh, it's the one with the variable in the denominator. No big deal. We've done these before. If you know the pattern, you can immediately jump to the answer. If not, do a little bit of algebra. Multiply both sides by x. The x's cancel. Divide both sides by tan 2. Tan 2's would cancel on the left side, so x is equal to 25 divided by tan 2. And we're done. So 700. Now, well, the only thing I would say is, give it is it a reasonable answer look? And so 715 meters away is reasonable. Remember, the angle is 2 degrees. So the lighthouse is pretty far away if the angle is 2 degrees. All right. The but here is that it could have been depression as well, too. So let's see how that works. So it says, calculate the distance between the sailboat and the lighthouse. So that immediately makes you thinking that your triangle is going to go from the sailboat to the lighthouse, but keep reading. If the lighthouse is 25 meters and the angle of depression between the lighthouse and the sailboat, angle of depression means you're looking down. So that means we have to look to the horizon first and then look down. So that is going to be your 15 degrees. If the lighthouse is 25 meters, well, then what's that black line that goes from the sailboat directly up? Well, if you thought about the previous triangle we just drew and you include this triangle, they do make, it's a parallelogram or a rectangle. Therefore, if the lighthouse's height is 25, then that black line over there would also be 25. And if we're trying to find the distance between the lighthouse and the sailboat, once again, that was our x for the previous problem. Parallelogram, opposite sides are congruent, so therefore the top line is also x. If that was stated too fast for you, rewind, play that one again. All right, so it's just a trig problem once again. The relationship between the two sides, x and 25, are the same as the previous one. It's the opposite and the adjacent. So we're back to tan. Tan is a very widely used, I don't know if it's, statistically the most widely used one, but we use tangent quite frequently. So let's see, tangent opposite over adjacent. This time it's not 2 degrees, it's 15 degrees, but the algebra is the same. We're still dividing this time not by tan 2, but by tan 15. Therefore, x is equal to 25 divided by tan 15. Toss that in, and there you go. So 93 meters. Ooh, we're pretty close. Now notice 2 degrees, we were pretty darn far away, but 15 degrees, right? The distance is a lot shorter. It went from 700 meters down to about 100 meters. If you think about it, if the angle is very high, then that object is very close to you. If the angle is very small, then it means the object is very far away from you. All right, one more. So it says a sailboat is 560 meters from the lighthouse. The sailboat or the lighthouse is 25 meters tall. What is the angle of elevation? Hopefully now you have a good feel for angle of elevation. So angle of elevation must come from the sailboat to the lighthouse. Lighthouse is still 25 meters. The angle of elevation from the sailboat is what we're trying to calculate. So that will be an x. But the other piece of information we're given is that the sailboat is 560 meters away. So that would be the blue line right there. All right, I put an M there. I should have put an M. Excuse me. All right, so let's see. What's the relationship here? Oh, it's still tangent, opposite and adjacent. So tan x is equal to 25 over 560. We're solving for an angle, so we're going to do inverse tangent this time. So inverse tangent of both sides. On the left side, inverse tangent and tangent are inverse operation of each other, so they would cancel. You'd be left with x, and the 25 over 560 is what you would toss in. So therefore, x is about 2.6 degrees. So let's see, at 2 degrees, we were 700 meters away. At 2.6 degrees, we're closer, and we're 560 meters away. All right, last one. Actually, we've done this one before. I had this in my presentation because when I actually taught this to the kids, I didn't have time to do the castle one. I'll show you the castle thing again. It's the same as it was from 2 days ago when we did tangent. So the problem with a trebuchet trying to knock down a castle wall is that it needs to know the distance. It can't just sit there in the open trying to shoot things at the castle, because the castle would send cavalrymen after them and it would get in trouble. It wants to knock the walls down quickly. So it needs to know the distance quickly between it and the castle walls. It can't just randomly throw stones. It needs to know this. By the way, if you were operating a trebuchet, you would know how much weight would throw a rock a certain distance. You can measure that before you went into battle. So you would go to the left or you go to the right a certain distance. Even someone who couldn't measure things accurately, you can unwind a piece of string that was 500 feet long, and you could get to that distance pretty quickly. You draw that triangle, you pull out your protractor, you measure that angle right there, let's say it's 56 degrees. Therefore, we can now calculate using a little bit of trig, it's tangent again, opposite over adjacent, in order to calculate that unknown distance. Multiply both sides by 500. So 500 tan 56 would equal to it. We've done this one before, so apparently I like 700. The sailboat one was the same answer as the first one, so 741 feet. All right, that'll do it for today. So that's it for the I was showing you in the class, I made an example of, we don't have trebuchets, but we do have in the military, we have mortars, and mortars have to, when they aim their mortars, they have to aim at a specific elevation in order for the mortar round to go a specific distance. And that's why that picture was there. Okay, so that will do it for today. We will go over a review on Monday. And as I stated before, I'm sure we've talked twice this week, so hopefully things are going well with you. And I will let you go.